Hey there, let's talk about IBIS. My name is Patrick. I am a product manager at Voltron Data. My background is in analytics, process improvement, and automation. Typically, I'm an engineer around like streamlining workflows for analysts and data scientists and data engineers and ETL developers. I've had all those hats, and I love automation. Um, but today, I work as a product manager for Voltron Data. I work with the SDK and IR team, that's the software development kit and intermediate representation team. And lately, their efforts have been focused on a project called IBIS. So in this video, I'll explain what IBIS is. I'll give a brief overview. I'll talk about the name, specifically what is an IBIS and how does it relate to the project. I'll give some code examples. What does IBIS look like in your .py files or your Jupyter notebooks? Then I'll go over a simple demo using an easy prompt of country data and a simple pivot table. And I'll provide two solutions to this easy prompt. First, the SQL string solution. This is the standard multi-line strings fed into a cursor solution. And then the IBIS solution, which is IBIS expressions to query data. I'll then make this easy prompt a little less easy by adding parameterization. So those SQL strings will become SQL F strings, and that IBIS code will just become IBIS code because IBIS accepts Python objects. The idea here being to demonstrate how stringly typed code, which is a phrase that I got from Philip Cloud, a contributor to IBIS, can make your data pipelines really complicated, the more complicated your queries get. So if you're using F strings, thing does the thing that you expect, checks types and references before execution, and then you execute. And IBIS accepts Python objects, so you don't have to do so much formatting. So let's get started. IBIS is an open source Python library. It allows for type-safe, light, and efficient ways of querying data using Python. It supports a lot of backends, namely SQLite, which is the base backend and the most well-rounded, DuckDB, which was added in 3.0, and this past April, that's April 2022. It also supports more popular backends like MySQL and Postgres. There are also some third-party supported backends like Google's BigQuery or OmniSciDB. You can find out which ones are contributor supported at ibisproject.org, or you can figure out which backends exist by looking them up on pypi.org or Conda channels. IBIS is heavily inspired by dplyr, so this is using code expressions to query or pare down your data before actually pulling it into memory. IBIS users consider IBIS to be pandas-like or PySpark-like, so there are column references using bracket notation, which is pandas-like. So you have your data frame or table expression, open bracket, open quote, column name, close quote, close bracket, and then that'll give you a column expression or a column reference. You could also use the attribute method. So you have, or attribute notation, which is equivalent in pandas, your call is equivalent in PySpark, your call is equivalent in IBIS. So object.fillNA, value. Next, you have some methods that are very similar in PySpark. So you have .filter, which will filter the data frame object. So the table expression .filter is your where clause equivalent, just like in PySpark. Your Spark data frame .filter is your where clause equivalent to PySpark. Same deal, select. So .select method will select specific columns that you care about. The goal of the project is to be a robust engine-agnostic Python SQL expression library. This is a mouthful. I made this phrase. I don't like it. The overall goal is engine agnosticism. That is a word. Engine agnosticism. So we want easily portable code. So suppose you have a personal project on a SQLite backend, so just a DB file in your local directory, and you want to upscale it because you think it's a good idea, or because you want to just upscale it, whatever. Whatever reason you want to move it to a different backend. So the ideal situation is you take your code, which is written in IBIS, And in order to migrate it, all you'd have to do is change the connector. So no matter what backend you're using, the code should just work, asterisks, because not all backends support all functionality, so there might be some gaps between different backends. In most cases, it should just be portable. And right now, the goal is to be a robust engine-agnostic Python SQL expression library. It's not robust right now, but it is open source, so if you see a gap in a backend that you care about, feel free to contribute by establishing an issue or joining in on the discussions or actually contributing some code. So easily portable code, that's the goal. So why is it called IBIS? Well, pictured here you see a small bird sitting on top of an elephant. Imagine a bird, I guess you could imagine like the bird is telling the elephant where to go, what to do, what to eat, what watering hole to go to. It's just chilling there, and the elephant is doing all the hard work. That's the idea behind IBIS. So we want lightweight Python code telling the backend to do the heavy lifting. So instead of, as I said earlier, pulling all your data into pandas or polars or some other data frame API and then filtering and transforming in memory, what you do is you just tell the backend to do the heavy lifting, and then you pull it into memory. And you do all this using Python expressions rather than using SQL strings. So you don't generate SQL strings, you generate Python code, and then you feed that code into your backend. So I didn't actually answer the question, what is an ibis? And pictured here is actually not an ibis. That is a cattle egret, that's a heron. Pictured here actually is an ibis. An ibis is a waterfowl with a hooked bill. They can typically be found within or around water. So here you see an ibis sitting on top of an elephant, and you can imagine the ibis telling the elephant where to go. Lightweight Python code telling the elephant what to do. Though, those of you that are paying attention, this is actually a watercolor, and it's a scarlet ibis. Those of you that know what a scarlet ibis is, those are native to northern South America. Those are actually not anywhere near any elephants, so this image probably would never happen unless an ibis found its way to Africa or India, or an elephant found its way to northern South America, probably in a zoo or something. Anyways, this is the inspiration for ibis, lightweight Python code down the backend to do the heavy lifting. When you use ibis, you could basically use it in as you would any other Python expression. So first you establish your connection. So on the left-hand side here, we have con equals ibis.sqlite.connect. So typically the syntax is ibis.backend.connect and then connection arguments. Connection arguments range from just one string. So here I have geography.db, which is a DB file in my local directory. You could also feed it, as you would in SQL Alchemy, a connection string. So for Postgres, it'd be like Postgres : host : port at username password. I don't actually know the syntax, but as you would with SQL Alchemy. Or you can use connection arguments like host equals, and then your host as a string, port equals your port as an int, username equals your username as a string, password equals your password as a string, hopefully not like in your script hard-coded, but whatever floats your boat, I guess. But yeah, connection arguments. Then once you have a connection established, you can run some pretty simple database commands like list database and list tables. These are each methods, and they return Python objects, so list of strings. On the right-hand side here, you see me establishing something called a table expression. This is an analog to a data frame. So what this does is actually pulls metadata from a table. So con.table table name gives me something called a table expression. And this is something that contains metadata for my table, and that is basically what columns are in there, what are the types of those columns, and that basically prepares me for, or prepares my script for running commands against that table, which I'll talk about in a minute. If I execute directly on a table expression, that's akin to doing select star from table, and what that does is it runs select star from table and then pulls it into memory into a pandas data frame. But if I wanted to filter down the table and maybe select specific columns, I could use the filter method, which accepts a column expression. So here I do select and filter equals countries.filter, and inside the parentheses I have a column expression that's countries continent using bracket notation. Pandas users will be familiar with this. And then on that column expression I have the isin method, and inside that isin method I have a list of strings. So this is equivalent to doing select from countries where continent is in AF. So this is your list of continent codes. And then on top of that expression, so countries.filter, open, close, that will give me a table expression. And that has a method called select. And PySpark users will be familiar with this. You can use this to select specific columns. Here I'm selecting specifically name. So countries.filter is countries where filter, so where continent is in AF. And then .select is select name from countries where continent is in AF. When I execute, I get the list of countries in my database whose continent code is AF. So these are countries that are located in Africa, according to my database. So to further explain IBIS in action, let's go over a simple demo. So suppose we have a database containing country data for 2017. Suppose there are two tables we care about, countries and GDP. They both join by ISO alpha 3 equals country code in countries and GDP respectively. Countries has a column called continent, which is a list of continent names associated to the countries in question. And GDP has a column called value, which is the GDP value for a country code. So what we want to do is we want to create a human readable pivot table of total GDP by continent for 2017. Continent codes are not human readable, so we need to wrap a case when statement around that field. So our query strategy is as follows. Wrap a case when statement around the continent field of countries to get continent names. Left join countries onto GDP in order to map values to continents, or countries. And we use the join key provided, so ISO alpha 3 equals country code. Then we will coalesce value in order to catch any null values, and we'll coalesce that to 0. So if it doesn't have a GDP value, assume that GDP value is 0. We'll then group by continent name, which is our case when result, and then aggregate our value, which is our coalesced result. And that's a sum, so group by and sum. Finally, we will display our result and then optionally export. Exporting is trivial, so I won't do it in this demonstration. The reason we use left join is because there might be continents fully composed of countries without GDP. For those of you that are familiar with geography, Antarctica might not have any GDP countries, so we want to capture all continents. Therefore, we want to capture Antarctica, and if Antarctica has no countries with GDP values, we still want to capture those, and we want to list it as 0. So let's get started. Alrighty, so our SQL string solution is pretty simple. It's 5 commands with a pretty simple query. I say simple because I've been using SQL for I think 8 years now, and this query was very easy to write. First, I will go line by line to demonstrate how tedious it is to read through these and to check them. Select continent. I don't know what continent is. I go to the first subquery. I see select case when, blah, 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 and then I see that alias is continent. Okay, continent is from the first subquery. Shoot back up to the top. Second select item is some coalesce value. I don't know what value is. I go to the first subquery. It's not there. I go to the second one. It's left joined, so there are possibly some null values in here. And then I see value is actually located in the second subquery. So that's where value comes from. I shoot back up at the top. I see it's aliased as continent GDP. I then go to the left join again. I see the on clause says country code equals ISO alpha 3. So hopefully country code is not null. If it is, then yikes, but it's not. Spoiler alert. Value is possibly null. So that's captured by the coalesced value back at the top. Good. Okay, so group by continent. If I don't know what continent is at this point, then I shoot back up to the top. I see continent is the first one. I see group by only has one item in it, so I want to make sure that all items are captured that need to be grouped. So I see continent is the only item that needs to be grouped. Okay, that's good. Order by 2, I don't know what 2 is. I shoot back up to the top. I see it's the continent GDP, which is our aggregate value. Okay, cool. 2 desk means descending order. All right. So that was just like a really quick rundown of the query. Suppose your query is more complicated. There's a lot more bouncing around. There's a lot more checking. So if you have more group by items, then you need to make sure that all the items are caught. You need to make sure that all items are within your subqueries or your from clause or your join clause, whatever. It's a mess the bigger the query gets. In this example, pretty simple, even though it contains a case when statement and 2 subqueries and a left join, but it's fine. It's simple. So when I fetch all my results, I get a human readable-ish list of tuples, and this contains my human readable continent names as well as my continent GDPs. Included at the bottom is Antarctica. So if we didn't do a left join, then that would not be there because they would all be null, or they would just not be present in my GDP table and therefore would be filtered out in a left join or in the inner join. The IDA solution, it's for a Python user, pretty simple. From top to bottom, you just import IBIS, you establish your connection, use the syntax mentioned before. You establish 2 table expressions because these are the tables that we care about, countries and GDP. So table expression on countries, table expression on GDP. I then want to filter on the year 2017, just as I did with the previous query. So GDP 2017 equals GDP table expression dot filter, and then column expression equals 2017. Again, I'm using Python objects here, so I'm using an integer, and that's fine. Continent name, here I'm establishing a case expression. With a case expression, I could establish when methods, or I can feed when methods onto it. So when NA, then North America, when SA, then South America, et cetera, et cetera, et cetera. Cap it off with an else underscore to give my default argument, so else bit, and then end it. It's similar to the SQL syntax, so case, when, else, end, and then name is your alias method, so name continent. After I've established my case expression, again, I'm not actually querying anything yet. I'm just establishing a bunch of expressions to prepare my query, and then when I run my query, that's when I'll actually execute and use resources. So after my case expression is established, I create my a new table expression, join. So countries left join GDP 2017. It's another table expression. My predicates are listed below. It's isoalpha3 equals country code. Cool. After I establish that table expression, so that has metadata in it, as well as the columns that are expected, given the table expressions that it is composed of. I can use that table expression join to create a column expression join value. That has a method called fillNA, which is cols. So join value cols to 0, so fillNA 0. And I can convert this to an aggregate expression using the sum method, and then alias that aggregate expression as continent GDP. Again, no resources being used other than what was used to get the metadata. And I am basically preparing all the items I need in order to actually create and execute my query. And I create my query, which is another table expression, result equals join dot group by continent name, which is my case expression, dot aggregate sum value, which is my aggregate expression, sort by, which is a method on a table expression in order to sort values by some column, continent GDP, which is the alias for my aggregate expression. False is the second argument in the sort by method, which is ascending equals false. So Pandas user will be familiar with that. And then after you've established your table expression, you can select specific columns from it by feeding it into bracket notation, not similar to Pandas. It's just single brackets, continent and continent GDP. So it's just a list of column names. When I execute this, I get a Pandas data frame back of my human readable continent names and my GDP values that are not so human readable, but they are numerics. So they're human readable enough. Side by side, I am excluding a lot of the code in the SQL string solution because it's very basic code. It's just connection, cursor, execute, and import. So on the left, we have a query that can be kind of tedious to check and read. So if I were a new grad or a new employee or a programmer that's not really familiar with SQL, it would take me a while to dig through this and figure out what's going on. SQL is pretty easy to learn. It's just really tedious to read and check. Even as like an 8-year user of SQL, this is not something that I'd want to do on a regular basis. But whereas on the right, we have Python expressions, which is, or IDIS Python expressions, um, which are much easier to read for programmers. Even if you're not familiar with Python, but you are familiar with some other API or programming language, you should be able to figure out what's going on here. So you establish something called a table. You filter one of the tables by some value. You do some kind of case thing on some kind of like column thing. And then you alias it with a name. And then there's something called a left join. Basically, if you know the gist of SQL and you know the gist of Python, you can eventually figure out what's going on line by line. You're not bouncing around. It's not tedious. It's just code. And now let's make this simple demo a little less simple by parameterizing. So suppose we want variable continent definitions. So instead of just bucketing with standard definitions for continent code to call continent names, we want to bucket continents arbitrarily. So suppose we want Americas and we want to map NA and SA to Americas. We can do that with the variable continent definition. Suppose we have variable years. Suppose we have more years than just 2017 in our database and we want to arbitrarily define sets that we want to aggregate. So if we want to do just 2017, that's fine. If we want to do 2017, 2018, we want to do that as well. We also want call list values, arbitrary. So instead of assuming that a continent missing a GDP value is 0, we want to be able to assume it's like some negative value, or maybe it's some positive value, just some arbitrary value. We just want to make it variable for fun. So parameterizing SQL is pretty straightforward. You have your mapping. First, you establish a mapping, so you can bucket your continent codes to continent names. Here, I'm just doing the standard NA to North America, SA to South America. You establish an empty list, so you can loop through your mappings and feed in some when statements, so you can format them later. You establish a when skeleton, so when continent equals continent code, then continent name. New line to make sure that there's some empty space between when statements. You loop through your mapping in order to feed a formatted when statement. So when NA, then North America. New line, when SA, then South America. New line, when EU, then Europe. New line, etc. Once you have your list composed from that when for loop, you join them together using the string join method. And this basically just puts them into one string, or compiles them into one string. You can then format a case else skeleton using that when string. So you have case when NA, then North America, new line, space, when SA, then South America, new line, space, ... else unknown continent, end as continent. That will give you your case when statement and given some arbitrary buckets here. So if I wanted Americas, I could do NA Americas, SA Americas, and then here it would be case when NA, then Americas, new line, space, when SA, then Americas, new line, space, etc. Finally, I can create my arbitrary set of years by feeding in a list of integers. So if I get a list of integers, so 2017, 2018, I can use the join method on a string to format a comma delimited list of integers into a string, so I can feed it into my query. And finally, my call list value is just some numeric that I can feed into an f string. So on the right here, you have your f string, which is your skeleton for your query. This can accept your call list val, your case when statement, and your year vals. Call list val being your case when statement that is formatted. Your call list value, which is your numeric, your case when statement, which is your formatted case when statement skeleton, and your year vals, which is your comma delimited list of integers into a string. And then when you execute, you actually get this error. So if I wanted to check this error, what I would do is I would start at the bottom and I would see no such column continent. Okay, clearly there is some typo somewhere. So go to the top, go line by line, call list val equals 0, SQL open string, select continent, ... to desk, close string, result equals cur execute SQL. Okay, so this was not helpful since continent does not equal continent. I know there's a typo somewhere, but this error, this stack trace did not help me at all. I will give the user a second to figure out what went wrong. All right, so those of you that found it, it's actually right here. It's right there, there's a T missing in my continent. So syntactically, my Python was fine. My code ran just fine right up until execution. So I actually had to query data or try to query before I figured out that something was wrong. And then when my kernel figured out, hey, something's wrong, it threw me a stack trace that wasn't very helpful. So I had to read line by line to figure out, well, what went wrong. So that's the SQL string solution with just a small hiccup that can make things tedious, annoying to figure out. Parameterizing IBIS is roughly the same method, but it's easier because IBIS accepts Python objects. First, establish your mappings, just like you did before. Then establish your coalesce val, which is some numeric, and year vals, which is some list of integers. Cool thing about IBIS is, like I said, it accepts Python objects. So you don't need to format any year strings. So you don't need to do comma, join, and then list of integers. As before, you establish your table expressions, and then you can filter GDP using the isin method, as I showed you before, which accepts just a Python object, so a list of integers. So GDP year is in your year vals. You can then create case one statements using the cases method. Here I feed a list of tuples. These are my mappings. So dictionaries have a method called items. And this gives you key value pairs in a list. So feed that, and that creates my list of when statements. So instead of looping when this, then this, when this, then this, I could just feed the items into a cases method to create my case one statement, my case one expression. Unknown consonant is the default value, so else unknown consonant, and then .name is my alias. And then when I run this, I get this error. Shoot down to the bottom, value continent, okay, typo, is not a field in ISOAuth 2, ISOAuth 3, isonumeric, fits, name, capital, area, KM2, population, continent. Okay, so clearly continent is supposed to be continent. Where is that supposed to be? Shoot up to the top, 19, GDP, table, GDP 2017, GDP, filter, GDP year is in year vals. 23, continent name equals country's continent. Cool, so not only did the stack trace tell me that there was a typo just like the other one, but it actually failed on the line that it was supposed to fail at. So instead of waiting for execution, it failed on the typo line. And that is located right here. So I didn't use any resources other than pulling metadata before figuring out, hey, there's a name reference issue here, fix that. So what I would do is I would put the T there, and then I would run my code, and then it would go line by line and do name reference checking and type checking before actually trying to use any resources to run a query. So side by side, suppose you're a new graduate or a new user to SQL or someone who's never used SQL. Like I said before, I am not harping on SQL. SQL is very easy to use. It's a very transactional language. You select things from places, where, conditions. You group by if you need to. You order by if you need to. Having if you need to. It's a very English language for English speakers. It's very easy to use. But it's tedious to check. It's tedious to read. I like writing SQL. I don't like reading it. I think I could probably count on both my hands the amount of times that I've written really long queries and then actually read them again. So like I just cowboy code them and then just like let them collect dust while they work in the cloud. So it's not something that I like to revisit. Whereas with Python code, I check it on a regular basis. It's very easy line by line to go through. So on the right here, you have your IBIS expressions, which are all Python. If you are a new student, like a new graduate student or like an intern or something, and you're familiar with programming languages like Python or R or say MATLAB, you might be able to pick this up a little bit easier. I mean, it might be difficult at first, but over time, the more Python you write, the more Python you read, the easier it'll be to read the thing on the right than it is on the left, because it's going line by line, top to bottom. And if you see a reference that you don't really remember, you could shoot back up to the definition, and it's code. Whereas in SQL, you're bouncing around all over the place. You also fail a lot easier. So with IBIS, you have type checking and reference checking, and no resources are used until um, no resources are used until you tell it to use resources or until it can use resources. Um, so suppose you have a complicated workflow of 2 or 3 queries. The first query is fine. It runs fine. So you execute that query. Second query, it fails. So in the SQL string solution, your Python might be syntactically okay. So your string generation is perfectly fine. And your code executes great right up until the second query's execution. Then you have to go line by line. If the stack trace is not helpful, like the one displayed here, then you have to go line by line to make sure that there are no typos. You have to make sure that your types are right. You have to make sure your name references are correct. You have to make sure that your subqueries contain all the references that you care about. It's annoying. It's tedious. I hate doing it. So you do that, you iterate over your second query until it works. And then your third query, right? If you have a third query, that one fails. And then you do the same thing. And each time you iterate, you're actually using resources for the first 2 because the first 2 are running before you run your third one. In IBIS, you can define all of your expressions up front and then execute your queries. And then that will use fewer resources as you're iterating. And, extinguishing these very simple references to names or types. So generally, IBIS allows you to fail smarter quickly using type checking and reference checking. It's a lot easier for Python users to read IBIS expressions versus reading SQL. So swapping between Python and SQL can be kind of like an annoying mess and can lead to developer burnout. So you want to try to avoid this as much as possible. You can convert all your code to IBIS, and then they're just reading Python code. And Python expressions will fail line by line. Again, fail smarter quickly. And then lastly, IBIS, the goal is engine agnosticism. You want easily portable code. If you have a project in one place and you want to migrate the backend to another place, the idea is instead of like going through this whole period of like checking all of your queries, making sure the syntax meshes well between backends, if IBIS supports both backends, ideally you would have minimal code change. So you would just swap out the connector and then your code would work. IBIS is open source and public, so please contribute. Contributions are not limited to code contributions, but they do include issue creation and discussion participation. Simply downloading the package and like using it and poking holes in it, that is contribution enough. Please use it. It's a really awesome package. As for why it's included in the data thread and the Arrow ecosystem, well, this year, we plan on having IBIS substrate support. So with substrate support will come Arrow support. So we can go from IBIS to substrate to Arrow, and Arrow to substrate to IBIS. Now, this isn't limited to Arrow, because substrate is an engine-agnostic way of communicating between APIs and engines. So you can go from IBIS to substrate to DuckDB if you wanted. I don't know why you'd want to do that, but it's possible. So anything that supports substrate, IBIS can theoretically then support. Now, there's an asterisk on that. It's not done yet, but just keep tabs on it. We will have blogs on the IBIS website, so ibisproject.org. And for those of you that are interested, there's something called the Voltron Enterprise subscription for Arrow. There is a free tier to this, which allows newsletters and announcements. I think Voltron will be giving shoutouts around IBIS and IBIS announcements. So check out voltrondata.com/subscription to look at the various tiers for Voltron subscriptions to analytics or Arrow. Again, this is not paying for IBIS. This is just Voltron's way of communicating or announcing various things that are interesting about the Arrow ecosystem, and IBIS is included in that. So check it out. Thanks for listening. My name is Patrick, and this is a logo by Tim Swast from Google. I like it. It's a pretty little picture of an IBIS. Thanks.